All right, this podcast is going to be on taking electron configuration from the first year chemistry level to the AP level. So previously with electron configuration, you knew that there were levels for all of the orbitals in an atom. And just drawing out a couple of the levels, we have different types of orbitals. We have s orbitals. We have, let's see here, 1, 2, 3, 4, 5. Okay, so we have S, we have P, and we have D, and there are energy levels that they are located in. Well, now what we're doing is we're actually assigning letters and numbers to describe each of the things involved with electron configuration. So these energy levels, which is how far away you are from the nucleus, is what we call the principal quantum number. So N is our principal quantum number. And the principal quantum number isn't any different than the energy levels you had learned in the past. So they start at 1 and they go on as essentially as far as you want. We'll just say to infinity. All right. Now there's another quantum number that we need to describe, and that would be L. And L represents what's called the azimuthal quantum number. So the azimuthal quantum number, or L, what this tells you is, unlike the principal quantum number, which is focused on the energy level and how far away you are from the center of the atom, the azimuthal quantum number is the orbital shape. And what it does is it tells you the values or the number of shapes that you could possibly have at different energy levels. So for the azimuthal quantum number, those numbers go from 0 to n minus 1. So I'm going to give you an example of how you figure out the azimuthal quantum number. And how it would work is, say you have an atom that has 3 as n. N is 3. There's 3 energy levels. So L would have values of 0, 1, and 2, not 3. So remember, it goes from 0 all the way to n minus 1. If n is 3, the highest you get up to is 2. Now, each of these azimuthal quantum numbers represent the shapes of the orbitals. 0 is the s orbital, 1 is the p orbital, 2 is the d orbital, and if I was dealing with a n equals 4 atom, the azimuthal quantum number, if it was 3, would represent, of course, the f orbitals. Now let's talk about another quantum number. This quantum number is m sub L, which we call the magnetic quantum number. All right, and what the magnetic quantum number tells you is the orientation of the orbital. Now don't forget, there is a center to an atom, and there are 4 axes, x, y, and z. So if I was a p orbital along the x-axis, I would be p sub x. So the magnetic quantum number allows you to predict the different shapes. So the numbers work like this. The magnetic quantum numbers go from negative L to L. All right. Now, this does include 0. So when you're going from negative L to L, don't forget to write 0. So let's do an example of this one. So in this one, let's say I have an atom that has N as 3. Okay, so don't forget I've got to have L, and as we learned, L goes from 0 to n minus 1, so it'd be 0, 1, and 2. So that'd be my S, my P, my D. And to figure out the magnetic quantum numbers for each of these, so this one would just be 0, because it's negative L to L, and L for this one will stay 0. For the 1, it would be negative 1, 0, 1, and for the 2, it would be negative 2, negative 1, 0, positive 1, and 2. So if you're wondering, what the heck do all those numbers mean? Well, remember back in the day in your first year chemistry course, you learned that the s orbitals, there's only one orientation for the s orbital. For p, we learned that there are 3 orbitals. There's the px, py and the pz. For the d, there is the dxy, there is the dyz, there is the dxz, there is the dz squared, and there's the dx squared minus y squared. So in any case, what each of those numbers, those quantum numbers, represent is that each of those electrons would be at a different energy level, and that would be the magnetic quantum number. So those magnetic quantum numbers represent the different orientations around the center of an atom. All right, we still do actually have one last quantum number, and this one is called the magnetic spin, and it's represented as ns. So we call it the spin magnetic quantum number. Now, the spin magnetic quantum number has values of plus half or minus half. And that's where we get the half arrow up or the half arrow down when we're drawing electrons in orbitals. Then there are two rules that you didn't actually learn about in first year chemistry, but you learned the rules, you just didn't actually know the names of the rules. One's called the Pauli exclusion principle. And the Pauli exclusion principle can be summarized as no two electrons have the same energy, which means all of their quantum numbers must be different for every electron. So what does this really mean to you? Well, remember back in the day, you had the box orbital notation, and say this was the 2s and say this was the 2p. What this meant is that when I'm filling in the 2s, the first electron goes in with a half spin up, the second electron half spin down. That right there is the Pauli exclusion principle, that for each orbital you have to make sure that the spins are opposite of each other. Then there's this rule that we haven't learned about, but you understand it already, believe it or not, and when I explain it to you, you'll be like, oh, that makes a lot of sense. The Hund's rule is that spin is maximized. So I used an analogy in my first year chemistry course saying that when you fill in the electrons for the 2p orbital, think of them as rooms in a 3-bedroom apartment. So the people spread out first. First electron on the 2p goes there, the second goes there. Well, what that is the Hund's rule. You want to maximize the spin first before you start drawing those electrons pointing half down. And then, of course, don't forget that if you ever hear anything talking about the outer shell electrons are the same as valence electrons. They're exactly the same thing. All right. There is a tad more that we need to cover, and this time I'm going to be getting out a blank periodic table. So with my blank periodic table, I'm going to be identifying a couple exceptions to the rules that you learned. So we learned that the periods going across the periodic table can also be considered the energy levels, but then don't forget when you get to D, they're all one energy level less. And then when you go back to the P, they go back up again. So here's my S, here's my D, here's my P, and here's my F. Well, now I actually have to teach you about the F orbitals. The F are one energy level less than the D, so it's 4 and 5. And just like you had 5 boxes for the D, well, if you count, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There are 7 boxes for the F, 7 orbitals in the F region. Now, let's talk about the D. And by the way, you could figure that out with what I had just taught you with dealing with the quantum numbers. With the azimuthal quantum number, you could figure out the number of orbitals that are actually there, along with the other orbital that I was talking to you about, which is the magnetic quantum number. Based on that tells you how many orbitals are in that shape. So 0 is a shape, 1's a shape, 2's a shape, and the numbers that you derive it from, that equation up there, give you all the different orientations for all the orbitals. So anyhow, F works the same way as all the other ones do. And basically, once you get to here, what you want to remember is that actually technically you have lanthanum right here and you have actinium here. And that's why we call this top row the lanthanides and we call this bottom row the actinides. So you would actually start filling in these guys after these guys. So look in your book. There'll be plenty of examples of that. Now what we're going to do is we're going to talk about some exceptions in the d orbitals. You should have read about degenerate orbitals and that there are a lot of energy levels that are pretty close to one another when you start dealing with an atom that has multiple electrons in it. The hydrogen, it's a very simple atom because you're only dealing with one electron. So all the orbitals at that n quantum number are always going to be at the same energy level. Since we're dealing primarily with lots of different atoms in chemistry, we have to learn how the electrons fill in. Well, there's actually an exception. Here's the exception. Say right here is actually copper, here's silver, and here's gold. AU. Okay? Well, if I was going to draw out copper's box orbital notation, I would go back to the last noble gas, which is argon. And for copper, I would write out Ar, and then it would be 4s2, 3d9. Well, see how it's really close to filling up all of the d orbital? Well, what happens is an electron jumps from the s orbital to the d to fill it up. So copper's electron configuration is actually, and I didn't tell you this in the first year chemistry course, 4s1, 3d10. And that's the same for silver, and it's also the same for gold. They're just one electron away from filling up all the d orbital, and that's what they do. And that's their full electron configuration. There's also another situation as well, and this deals with chromium and molybdenum. So let me count out where chromium and molybdenum are. So it goes scandium, titanium, vanadium, chromium. Here's chromium, and right below it is molybdenum. All right, so now I'm going to do a electron configuration for molybdenum. All right, let me start writing it out. Molybdenum's last noble gas is krypton. So MO, and here's my krypton Kr in brackets, and then it's 5s2, 4d4. If I drew out boxes for this electron configuration right here, let me draw out the boxes. It's an s, then it's 5 d orbitals. 1, 2, 3, 4, 5. So let me start filling them in. 1, 2, oops, sorry, this one's got to be down. Don't forget Hund's rule spin. Or actually, this is Pauli exclusion principle. Then 1, 2, 3, 4. Hey, there's one spot that's open on the d orbital. What happens for chromium and molybdenum is that the electron is transferred from the s to the d. So molybdenum's true electron configuration is actually Kr, 5s1, 4d5. So the reason why you weren't taught this in your first year is that it adds another layer of complexity because there are actually exceptions when it comes to particular elements in the periodic table. So now you should know the exceptions for chromium, molybdenum, copper, silver, and gold. And that's primarily the main difference in electron configuration between your first year chemistry course and now in AP chemistry.